So, you want to do linear regression. Now you're thinking to yourself, how in the world am I supposed to fit a line to my data points? Well, turns out there's lots of different approaches. Well, there's really one. It's the least squares estimator, and you can do that by hand if you're Gauss in the 1800s, but we have computers, so we can use computers to do this. So now that you have your computer ready, you can do some linear regression. But what tools are you going to use? You could use Python code or C code if you're a real programmer. If you wanted to, you could use a stats package like SAS or SPSS and I forget. There's lots of S's, it doesn't really matter, because what we'll be using is R. R is a great programming language that's been around for many years. It's open source, has a lot of users, specifically among academic and practicing statisticians. And that's what this video is all about. The idea is to talk about how can we use R to fit a linear regression. It's a little bit fast, but we're going to go through a quick introduction to how to install R, how to then start R, load data into R, and fit a linear model all in R. So, let's see what that's all about. Well, hello and welcome to another Cashlack lecture video. Today we'll be discussing something a little different. Rather than going through, say, some lecture notes, some material, some mathematical derivations, we're going to be focusing on R. Specifically, we're going to be focusing on how to use R to do linear regression, assuming that you've never actually turned on R in your life, because it turns out that I get the sense that some of my students have never done that before, so I thought it would be best to go through some very simple examples. First, how to install R, how to use R on the command lines, and then how to put data in, run a linear regression, look at the outputs, maybe plot a pretty picture. Seemed like a fun idea. So that's what we'll be doing today. Okay, so the first thing you're going to have to know if you want to use R to do linear regression is, how do you get R on your computer? Well, the first thing you should do is look up CRAN, or specifically cran.r-project.org. CRAN is the Comprehensive R Archive Network. It is your source for all things R. And the first thing you'll see on their main webpage at the very top is how to download and install R. So what you can do is you can pick your operating system and go through the, the example of how to install it. So for example, here we have my Windows machine, my little Surface laptop. And if I click on here, right, I have we have some binaries and some other stuff, but assuming you don't care about all that and you just want to install that, we can install R for the first time. And hey, what do you know, we have a download at the top. And presumably if I click that, yeah, I should get a exe file for my Windows machine. Now, of course, there's other ways you can do this too. If you're a real boss and you like to use Linux, then, well, there's lots of different varieties of Linux packages you can get. So you can go into Debian here and use all your really cool command lines to install R if you want to do it that way. Oh, and then there's also Mac OS, but seriously, who wants to use Mac OS? Get a better operating system. Anyway, after you've installed R on your computer, you can access it directly through command lines. So it depends on which operating system you're using. So if you're on Linux, you can just open a terminal, type R, capital R, and start R, and then be able to just work with it within a terminal. It looks pretty cool. Maybe it's not the cleanest or easiest way to use it, but it is fun. On Windows, you can start a GUI. It's not the prettiest looking thing, but you can use it to do R. However, probably the optimal way to do it, both for new users and for seasoned users, is to use RStudio. So RStudio can be found at, rstudio.com, and it is a nicer looking GUI that you can use to run R. If you go to download, what we should have is, choose your version. And once again, we have lots of different versions. We have the expensive Pro versions, but you don't need that. You just need the RStudio desktop version, which is free. And that's what we'll be using today in this tutorial video, so you can get a feel for what RStudio is all about. All right, so welcome to RStudio. RStudio is going to have a bunch of different windows, and when you start yours up, it might look a little bit different than mine because I have a ton of different R files open here in the top left. Now you can reconfigure the way these windows appear within RStudio as well. You'll notice in the bottom left here, we have the terminal. This is where all the magic happens in RStudio, right? Where I'm going to type in line after line. I preemptively typed in 2 lines here. I used the rm function to just remove all variables that were already saved in R, because as noted, R often will, you can save a workspace to R. So if you're RStudio, and actually base R as well, I mean, this is the same thing in some sense. So if you're using R, and you close it, you can save what you've done, all of the previous variables, the data you've loaded in, the commands you've run. They can all be saved in this .r data file. So basically, I removed that so that we wouldn't be confounded by any of the previous stuff that I already had in RStudio. And I also had to set a working directory, right? So R is going to default to whatever your home directory is, which would be, I guess, like a home directory on Linux. Probably the My Documents folder on Windows. Regardless, or irregardless, I should say, I have changed it to a different folder. So it's always good to know what folder you're working in, because that's where your R code files will be. That's where your data files will be. I should say, for this tutorial, I'm using this rtutorial.r that I created myself. It's up on my public website. I'll put a link down in the description so that you can download it yourself if you want to try this at home. We're also going to be using a data set. I think I called it usa.data. It's a bunch of demographic and voting data coming from the 2016 US election, presidential election. So we'll get to that later in this video. And that's also was uploaded in the form that I put it into R on my website, so you can find that and try it yourself if you're interested. It's kind of a fun data set, right? I always like to see, why are people voting for Trump or Clinton, for example, in 2016 across, 3,000 something counties in the US. It's good stuff. Anyway, so this is really what R is going to look like. On the right-hand side, we have, all the environment and history and stuff. You could probably just ignore that. The bottom right is going to be where we can get information. We can have plots. We can look at the packages that are installed. I have a ton of different packages installed on this, but you probably won't have as many if you're starting R for the first time. You can also look at help, which will tell us different manual pages. So I guess the last one I was looking at was the ACF function for computing autocorrelation. But what's really useful in R is that if you want a manual page, type ? And then type in a function. So LM is the one that we'll be using today. It's for fitting a linear model. And as you can see, as I type in ? LM, I get a very nice description on the right of how to use this function. Everything in R is a function. So, for example, even if you wanted to quit R, now this is a GUI, so I can just exit out in the top right. If you're running R on Linux, you can close your terminal, I guess, and just. But if you want to close R but keep the terminal open, you can type in Q with a open close parentheses. So it's kind of funny, but R, everything basically is some type of function in a way. All right, so now that we've done that, we're going to do what I said at the top here as very simple R. So the first thing I want to say is that R, again, is a scripting language, which means that I can write all this R code up here in the top left, but if I run this through R, it's just going to go line by line and say, run this line, run this line, run this line. Right? It's scripting, it's not compiled. If it were compiled, we would have to write the code, compile the code into an executable file, and then run it separately. So in this case, R is just interpreting line by line as we go. So I can basically use the print command, to print, let's do some arithmetic. I'm hitting Control Enter, by the way, which is going to take a line from the top left and run it in the terminal. So here, if I wanted to do simple math, I can use R as a glorified calculator, right? And say, 1 + 2 is equal to 3. And I can do more stuff, right? I can do 2 times 3, for example. I can do 2 divided by 3, you know, et cetera, et cetera. So if you type in a math equation, you're going to get something out. I think, let's see if we can do this. Nope, it's going to get mad. I think I need the quotes around it. There it is. Yeah, so here are a bunch of arithmetic operators in the bottom right. So if you want to find different ways to add, subtract, multiply, divide, exponentiate, I think the percent is doing like division, yeah, like with non-integer division. Yeah, so you can do some like whatever x mod y type things as well in R. Though I feel like if you're actually wanting to do a lot of like, you know, integer work and number theory, you might want to use a different programming language. R is very much designed, right, for you doing statistics. So it's great for statistics. Probably wouldn't use it for other things, but you can, right? You can run it in like batch modes and stuff and just have it, you know, as like an actual programming language, right? Anyway, so, right, you can use it as a calculator. Great. That's not too interesting. I mean, you can do that in anything like Python or Puri or whatever else you want to do. But we can also do sequences, say. So if I do 1:10, well, I just got a sequence of numbers 1 to 10. If I want to say go from 2 to 20, but only take the even integers, I can use the seq, the sequence command. And what I get is, hey, look, even integers. And if I want, I can also just use the C function, which is concatenate, and I can string together whatever integers or other, you know, real numbers that I want. So I get something like that. Now, let's say I have these 3 rows of numbers, and I want to put them into a table. So the next thing we can do is we can use the rbind function, which is row bind, which is going to put each of these 3 sequences of numbers into sequential rows in a table, 1, 2, 3. So I get something that looks like that. Now I have a 3 by 10 table in R, where each row is going to correspond to one of these sequences that I just created. I can do the same thing with cbind. Cbind is going to do the exact same thing I just did, but make them into columns. So now the first column is 1 through 10. The second is 2 through 20 even numbers. And the third is just all the, you know, random integers that I just wrote down, like arbitrary integers. So in R, you can have a table. You can also have a data frame. You can have a matrix. You can have an array. You can have various list objects. It's actually super annoying because certain functions are only going to want certain types of data structures, and they're all kind of the same and yet kind of different at the same time, which is super frustrating, especially if you're familiar with languages like C or C++, where everything is very precise. If you define a variable as a certain thing, it's that thing, right? It's not... is that called strong typing? I forget. I'm not actually a computer scientist, so I forget some of these terms, but... right, in R, you can kind of just say, it's a table, oh, now it's a matrix, now it's an array, you know, whatever, it's a data frame. So you probably, as you start to use R, will have to fight with the data types, but hopefully it's not too painful for you. Anyway, we'll do a little bit more arithmetic. It's kind of boring, but it's good to show you some examples. The next thing we have here is we can add and multiply tables entry-wise. So I'm going to create 2 tables, tab 1 and tab 2. Tab 1 is going to be, well, the numbers 1 through 9 going row-wise. Tab 2 is the numbers 1 through 9 going column-wise, so not that interesting. But if I use the addition sign here, I'm effectively adding these 2 tables or matrices together. And I get the answer out. Great. If I use multiplication, the star sign, what I get is I get entry-wise multiplication. This would be the Hadamard product, if you like that terminology, or the entry-wise matrix product. This is different, right, than doing matrix multiplication like we would want to do in a linear algebra class. If we want to do matrix multiplication, we want to use the %* operator, which is going to say, no, don't do this entry-wise, but treat this as matrices. So if I do this, I do matrix multiplication, and I get out a very different answer than I did when I did entry-wise multiplication. So it's good to just be aware that you're doing the right type of multiplication that you think you're doing or that you want to do. That's going to be important. Right, so R, again, is very much a statistical programming language, which means you have some very nice built-in functions here for generating random numbers. Right, this is going to be a big piece of doing any type of simulation study that you might be doing, is to generate random numbers. So this example would be, how do I generate 10 random standard normal random variables, mean 0, variance 1, and I can use the rnorm function right here. That's going to, well, as I say, the longest, this is going to give me 10 independent random normal variables, right? Some numbers, on the real line, probably between plus or minus 3 with high probability. Anyway, I have 3 arguments that go into this function. N is going to be the number of, well, actually, I'll just do this, question mark rnorm, and then you can see it over here. N is going to be the number of random variates I'm going to generate. The mean I'm setting to be 0. The standard deviation I'm setting to be 1. I point out also the hash symbol here is going to be a comment, right, in R, which is why you see all up in my code here these green lines, which is basically comments. Don't call it hashtag. Please don't call it hashtag. That really bugs me. Anyway, yes, so in this case, what we're doing is we're using the longest way of writing this out. That is, I'm assigning each variable a value. I'm saying n is equal to 10, mean is equal to 0. I can do this shorter by just ignoring all of the variable names, the argument names. This only works if you get it in the right order, right? Whereas for the longer, if I go to this longer command up here, I could, for example, rearrange this. And as long as I tell R which argument has which value, it doesn't matter what order I put it in. Whereas if I tried to do that here and say 0, 10, it's going to probably get mad at me because I'm saying generate nothing. Yeah, so it just gave me a numeric 0, which I guess is an empty, some sort of empty object, right? It's kind of like the null set, I guess, in R. Also, a lot of R functions will have defaults. So if I just say rnorm 10, that's also an equivalent command line, because if we go over to the documentation, n is not set. So I have to tell R what n is, but the mean defaults to 0. The standard deviation defaults to 1. So in that case, if I just say rnorm 10, it's going to generate 10 random variates with mean 0, variance 1. Standard deviation 1, but same thing, right? Let's see, what else can we do? Well, you can also remove all these really annoying long decimal places, because seriously, who needs that many decimal places? It's like annoying to look at. You can use the round command, the function, and then assign a certain number of digits. So if I want to round to 4, if I want to round to 4, right, I can do that. And now I have my 10 random normal variates, but I'm only keeping 4 decimal places. So it's a little bit nicer to look at. And especially good if you ever want to export your data, your simulation and stuff into a document, a research paper, or some report. It's nice to not just include tons of decimal places because they don't matter and it's just going to make everything look really messy. Anyway, yeah, so what else can we do? Well, if you're trying to reproduce the same random simulation, you might want to use the set seed value. So if I set a seed, that's a random seed for R. And then if I generate something like this, I get, okay, here's 3 random normal variates. What if I reset the seed to 191, and then I once again try to generate this, I get the exact same random numbers again, right? So I got the random numbers twice. This is important because if you're trying to simulate data and you want to be able to reproduce, like for example, in a lecture or something, the same results every single time, it's good to set a random seed. Otherwise, every time you run your code, you might get a different output, which is probably what you would want if you're doing large-scale simulations. But if you're trying to do this more instructively, then it's always nice to know how to do that. Right, so we can also do other things. We don't just have to do the normal distribution. We can do the binomial distribution. Our binom is going to give us a random binomial variate, in this case, 10 of them. Size n is equal, n is the sample size, but the size of the binomial is going to be 25, and the probability of getting a success, right, is going to be 1/3. So this is equivalent to saying I'm flipping 25 weighted coins. The probability of getting a head is 1/3. How many heads do I get out of when I do this? And I get, 8 heads, 4 heads, 9 heads, etc. So shifted a little bit to the left because the probability of a success is less than 1/2. Anyway, that's basically all the little commands you can use in R. Not all the commands you can use in R. Those are all the commands that I really care to show you in R. There's tons of stuff, right? And you're welcome to go in and look to see what you can find yourself. For example, just typing stats, which is one of the main packages, : you can get a big old list of different R commands. There's tons of different stuff you can do, and you'll have to explore yourself to figure out what type of commands you want to use for the given data problem or study that you're doing yourself. For the rest of this lecture, we will be moving on to regression in R because that's going to be the topic of this course. All right, well, let's do some regression in R, right? Because that's what this is really all about, is giving you some basic tools for how to do regression in R. Well, the first thing you're going to need to do is get the data into R. So I have a file called usadata.csv. CSV is a comma-separated variables. Whatever it is, it's like a spreadsheet, but you use commas as the separator. So in R, there's lots of read.somethings. Let me try and get this for you. If I type read dot, right, I have ftable, CSV, CSV2, dlim, dlim2, whatever diff is, Fortran. I guess if you really wanted to read in Fortran code into R, apparently there's a function for that. Fixed width, format, there's lots of stuff. One of the basic ones is read.table. So if we look over here on the right, we see the explanation of what read.table is. Note also that when you see a manual page, it will tell you which package the function lies in. In this case, it's in the utils package. There's a bunch of packages that are installed automatically in R. And then, of course, you can install tons of other ones. If you go through CRAN, the repository online, you can find lots more packages. Probably you can find even more like non-CRAN repository or non-CRAN packages on GitHub and stuff like that. Anyway, read.table has a ton of different arguments because it allows you to read a variety of different types of files. But there's other things, like, again, you can have read.csv, which sets, say, the separator to comma, determines what quotations, tells you if there's a header or not. So you can play around with these. But for this data file, which, again, I said is available publicly on my website, it was something that I kind of like concatenated together from other sources. So just to make sure my sources are covered, right, I downloaded some data from the US Census, publicly available, and also some voting results of the 2016 election, put them into the same CSV file, and made sure that all the counties in the US line up. So anyway, let's load this in. So I run the command, I load this in. Note that you need to have this file in your current working directory. Again, you can use get wd to figure out what your current working directory is. And otherwise, you could give a path here. So you could have a path like, /my data / folder / whatever to tell R where to find this file. Anyway, I just have it in my current working directory, so I don't need a path. So there's a couple useful things. Like the first thing you do when you load a data set into R, I would say, is probably you should look at it and just see what you got, right? It's always good to look at your data. The first thing we have here as well, we can use the nRow and the nCol functions to figure out how many rows and how many columns do I have. Well, I have a little over 3,000 rows. Each one is going to correspond to a county in the US. And I have 16 different columns. Great. If you notice here, I'm using the print command just to print out a string. The paste command is going to paste multiple strings together. So I take my first string, I take a number, and I take a second string, and I combine them all into one string, which then I can print with the print command. Not strictly necessary in your own code, but if you wanted to print output, right, if you're running a function, it's always good to know kind of how to output some strings. Anyway, the head command is very useful because if I just type in head USA, then I get the top 6 lines of my data set. So here, what we have, we can see what our columns are. We have, well, the first columns don't really matter. The year is always going to be 2016 because I only took the 2016 election. The state, Alabama. The state as a 2-letter, I guess, abbreviation. The county name, right? These are all strings. I don't remember what FIPS is. I think it's some like county indicator. The total candidate votes. So this was data set regarding the number of votes that went to Donald Trump in 2016. So we have the candidate votes, how many votes Trump got, the total votes, how many total votes were cast in the county, the total population, including children and stuff. So not just voting population, but according to the census, how many people live in the county. We have the total people identified on the census as being male, the total people identified on the census as being female, the total people who identified themselves on the census as NHWA, which is non-Hispanic white male and non-Hispanic white female. So, you know, you can see kind of where I was going with this was I was looking at demographic information, thinking, well, why would one county vote heavily for Trump or heavily against Trump, you know, for Clinton or a third party candidate, you know, and are there any interesting demographic features that would affect that? We also have median income and the total area of the state. I forget the units for this. I should have double checked this before I started this video. I think it was square kilometers. I used a spatial package to create this in R. Well, the grid of the US was already created. I just used the code to compute the I believe it was square kilometers. Anyway, it means we have a lot of input. So let's say we wanted to predict which counties have the highest incomes or which counties voted more or less for Trump. Then we can use these other variables as predictors and say, well, what is the percentage of the population that identified themselves on the census as being non-Hispanic white? What's the total area? What's the population versus the total area? So if we wanted to look at population density, like these are all types of questions you could ask about this data set, which is why I find it really interesting. I originally used this for some spatial statistical analysis. That's way beyond the scope of what we want to do here. But yeah, spatial statistics is super interesting. So yeah, you can look that up if you want to. And if not, let me know and I'll point you in the right direction. Anyway, back to like simple R, now that I'm done with my little rant about the data set, we can use commands like mean, median, SD for standard deviation to get some information about our data set here. So I should also note that you can access a column in a data set using the $sign as an sort of, I don't know what the right word is, as a syntax, I guess. So if I type in USA here and hit $sign, it's going to try to autocomplete, and I can say, oh, I want state, right? And now if I print this out, it's just going to spit out a 3,108 long vector of state, so I'm not going to do that, but I can use head to give me the first 6 of them. So, and it's just Alabama, right? Because it's doing this alphabetically. If I type in length I should get 3,108, which is all the, basically it's taking this column here, the state column. What I'm doing in this command up here is, again, I'm using print and paste, and if you kind of work from inside out, I'm taking the total population, I'm computing the mean, I'm rounding it so I don't get an absurd amount of decimal places, and then I'm printing it all out. So we find out that the mean population across all 3,000 whatever counties in the US is about a little over 100,000 people. So, okay, that's pretty big. I mean, I guess counties are kind of big, right? If they have 100,000 people on average. But then you think, well, wait a minute, what is that? Is that really on average? If we compute the median, we get a much smaller 25,000. And if we compute the standard deviation using the SD command, we get, well, something like 300,000. So right away, if you see numbers that look like this, what's it telling you? It's telling you that the population is highly skewed to the right, which kind of makes sense. If we think about counties in the US, you're probably going to have like hundreds and hundreds of little small rural counties where nobody really lives. And then you're going to have a couple like massive mega cities like LA and New York, where you're going to have like 1 million or multiple millions of people in those counties. So we'll look at the data, and it's actually, why don't we just look at it now? I can plot a histogram. It's not in my command here, but it's easy enough to plot a histogram if I just type in USA dollar, what is it, total pop. And we get a really uninteresting looking histogram here, which is telling me that, yeah, sure, everyone's base, like most of them are really small, but it also stretches out pretty far. This is where you might want to do something like you do a log 10 transform. Log 10 would be basically doing a log base 10. And then we get something that looks more reasonable, right? So if this is log base 10, right, 3 means 1,000, 6 means 1,000,000. So you can kind of see this distribution of counties between 3 and 6, meaning between, say, 1,000 people in the county and 1,000,000 people in the county, with the sort of average being somewhere between 4 and 5. I mean, average, the median, I should say, the center of this being about maybe 4.5. So what's that? I guess somewhere between 10,000 and 100,000, which is probably our 25,000 right here. Anyway, yeah, this is just, again, ways to visualize your data. Another useful command that can be used all over the place is the summary command. So summary is one of these generic functions in R that can be applied to lots of different R objects. If you apply it to a data, just a vector of numbers, a list, I shouldn't say list. Lists are super annoying in R. That's a different thing. If I apply it to just a sequence of numbers like total populations and hit summary, it's going to give me the minimum coming in at only slightly over 100 people. It's going to give me the max, which is like 10 million. It's going to give me a mean, a median, a first quartile, and a third quartile. So it kind of just spits out a quick summary of the numbers that you gave it. The summary command will come back later because you can use it to get information about a linear model or other things. Note that it's a very generic thing. It just says summary object. So very often if I download or install a new R package and I run some command, I often will wrap it in a summary just to see if it's going to, if the output can be summarized, or if the coder took the time to give a summary. We'll see more examples of this in a second, but you'll see this a lot in R where you have these generic functions. Predict is another one because you can fit tons of different statistical models in R, and you can almost always often use the predict function to do a prediction. Depending on the object, the model that you fit, predict will behave differently. So it's always good to know kind of what you're doing. Anyway, that's that. We still haven't gotten to linear regression, but we're still looking at this data set. If we want to, say, find the county with the minimal population, my code is running off the end of the screen here, we can use which.min. So which.min is going to return, I'll just, I'll run this command and show you what it looks like. Which.min here is going to tell me that the minimal population is in row 2,640. Great. Okay, don't know what county that is, but that's what it is. The maximal one is going to be in row 176. So again, which.min and which.max are going to return the index of the min and the max entry. These are really useful commands to know. If I wrap them in a concatenate, a C, and I put them in, try to take out those values from the USA data set, I get two rows. It's kind of hard to read, but the first row here is going to be Loving County in Texas, which comes in at a population of 117. The second row is going to be Los Angeles County in California, which is coming in with the maximal population of about 10 million. So again, very big differences in population from county to county, because county is not a very well-defined standardized unit, right, in the US. Anyway, another thing to note here is that I used USA square brackets. So the USA table, again, is going to be a 3000 whatever by like 16 table. I can access an element in it by using row and column indexing. So if I want to find, let's say, the 100th row and the 4th entry, I find out that I'm in the state of Arkansas, I guess, for better or worse. If I go to 6, I guess I'm in, I don't know what, Crittenden, I guess, county. Don't know where that is, but, maybe one day I'll go there. Anyway, it's just like a row column index, so it's pretty simple to just type in a row, a column, and get out, whatever entry in the table you want. If I leave the column blank and I just give it a row, then I get, I typed in 10, so I got a county in Alabama. If I type in 100, I get that county in Arkansas. If I really wanted to, I could get a column out. I don't really want to do that because it's going to spit out 3000 things into my R output. But if I were to hit enter, I would get, I can't type in 100. That's silly. That's out of bounds, right? So it's just going to give me an error. But if I wanted, let's say, the vector of all possible counties, I could access it by saying USA, 6. Again, let's just wrap it in a head so that you can kind of see what this is. So this would be a vector of all the counties. I can also access that again using the dollar notation and saying county because I labeled the columns. If you don't label the columns, you can't do that. But just different ways to get the exact same thing in R, depending on what the usage case. If you're writing formula, it's very nice to use column labels. If you're coding and iterating through columns, then you probably want to use numbers. But again, it all depends on your use case. The which command is a very useful one. So here, right, if I want, I can use which to extract indexes, right, that correspond to a Boolean. So if, for example, I take the total pop here, total population, and say less than 500, well, now I'm going to get a big vector of true and false values. It's basically saying, is the population less than 500 or not? True, false, true, false. Again, that's going to be a 3108 long vector. If I wrap it in a which, it's going to tell me which of these are true, and it's going to spit out a couple numbers, right? So in this case, I only have 6 numbers here, and these are corresponding to the rows of the 6 counties with populations under 500. So if I run this command, again with a column here, to basically have an empty columns, so I want all columns for only the rows where the total population is under 500. And if I do that, I get, 6 rows and a couple counties, Montana, Nebraska, a few in Texas, right? And these are all the ones where the total population variable lies strictly less than 500. So again, these are all good ways to manipulate your data. We're finally going to get to that linear regression, I promise. I think we're just about there. Now that we've done a lot of, basically querying the data set, right, by asking, which counties have small populations, which have large, we can also do a scatter plot, which is a really useful way to visualize the data. Actually, the first thing I'm going to do is we're going to get rid of this command. So if I do a scatter plot, it's going to look something like this. This is population versus median income. Let's give ourselves a little bit more room over here. So if I plot population versus median income, well, okay, you kind of see this right skewness here, where we have lots of counties with a very small population, and then LA way out here on the right. I think some of these ones around 1 million are going to be like New York and the Bronx, if I recall correctly. But I haven't looked at this data set in like 6 months, so I kind of forget exactly which points are which points. What I wanted to get at here is that you can use plot to plot an x-axis and a y-axis, and you get a scatter plot. Is this the most useful way of visualizing the plot? Possibly not. Again, much like our histogram, everything is shoved over to the left, and that's not always a great way to visualize it. In R, if I use the log equals xy, I'm telling R that both the x-axis, the horizontal, and the y-axis, the vertical, should be plotted on the log scale. If I do that, I get a much, let's say, nicer scatter plot, something that looks like something we could draw a line through in a linear regression problem. This is kind of more advanced linear regression, but oftentimes you might want to consider transforming your data before fitting a linear model to it. In this case, I'm kind of jumping ahead to the answer, which is do a log-log transform, because both population, we have lots of small population and a few giant populations. And similar with income, we have smaller incomes, some really big median incomes in counties. So oftentimes a log-log transformation will help make the data more palatable for fitting statistical models. Not always, right? You have to think on your feet a little bit about how to get your data into a good form before analyzing it. Nevertheless, this is our scatter plot. It looks much nicer now. And again, the x-axis and the y-axis are both on the log-log scale. If I want, I can compute a correlation using the core command here. And notice that I'm computing the correlation on the log scale. I'm using log base 10 because it's a little bit easier to digest if you're not good with, well, log base E is great for math, but it's kind of just annoying to look at. Log base 2 is great if you're happy doing powers of 2 in your head. So if you're a computer scientist, you probably want to do log base 2. If you're a physical scientist, you probably want to do log base 10. In math, we like our natural logs, of course. So it all depends on what you want to do. In R, you can do log 2 for log base 2 if you want. And I guess you can even do like other types of logs and stuff. There's log base 2 and log base 10, which are the standard ones. And then, of course, log for the natural logarithm. Anyway, there's a correlation of 0.4116. Recall that correlation is a measure of the linearity between two data sets. So it's kind of saying that, yeah, okay, it looks like there could be some linear relationship here. This is different than than fitting a linear model, but it is somewhat related, right? Linear models, correlation, they're both looking at linear relationships between the x and y coordinate. Anyway, after whatever we're at now, it looks like 40 minutes in R, and yeah, lots of time on the clock already. We finally get to the LM function, the great LM function, which is going to fit our line to our data. So in R, if you want to fit a linear model, you're going to need to give it a formula. Formula objects, well, can be super annoying to write. If you want to see some real headaches, go look up things like mixed effects models in the AOV function, the ANOVA command, and you can find some really crazy like nested factors, and oh, it's just the worst to try to figure out how to write it. In this case, it's actually pretty simple. We use the tilde to mean equals or related to. So that's the most important thing. A formula in R does not use the equal sign, it uses the tilde. So when I write a command like this, what I'm saying is the input to my linear model is total population on the log scale. My output is total or median income on the log scale, log base 10 again for interpretability purposes. Notice that I didn't type in USA dollar here. You could do that, or you could just tell R, this is the data set, USA, that I'm working on. And then you don't have to continuously tell R where your variables are coming from. So let's do that. So, right, we can hit this, and Now we've just fit a linear model and we've saved it in the md.linear variable. So we go back to our favorite summary command and say, I want to summarize md.linear. And what do I get? A whole bunch of numbers. So let's look at this for a second. Okay, so we have the output of our linear model. What in the world is this thing telling us? Well, the summary, right, this variable here is going to be a list with lots of different things in it. I can access those manually with the $sign, right? And I can find things like coefficient, residuals, effects, rank, fitted value, like whatever all this stuff is. It's kind of a mess, right? The summary command is going to take all of that and spit it out in a nicer way of looking at it. But this is actually quite good. So what we get here, right? Let me see if is it going to resize it? No, it's not going to resize it. I'm going to run summary one more time so I get everything on the lines that I want. Anyway, the first thing it's going to tell us is, well, what did you actually type in? So it remembers the formula that we typed in case we have lots of models and we're trying to remember, well, which one is which. It has some information on the residuals. The residuals, right, are the difference between the points in the data, the observed data, and the fitted line. And this just gives us an idea of, well, do our residuals look roughly, centered around 0, right? The median is super close to 0. That's a good sign. I don't see any like strong skewness or anything in the residuals, so that seems to be helpful. But honestly, this isn't the most useful thing. There are other plots you can use for analyzing residuals and goodness of fit, which will be a discussion for later. Most importantly is our coefficients. Our coefficients are going to give me an intercept term and a slope, right? Because I have one input, one output to my model. So basically I have a slope and I have an intercept. The intercept, I guess, is going to tell us what the median income should be on the log 10 scale if the total population on the log scale is equal to 0. So what's that mean? Well, that means that if I have a population of, I guess, well, what's log, right? If the log of the population is 0, that means I have one person in my county. Not the most interesting thing, but, whatever, it works. And what that means is that if I have my one-person county, we would predict that the median income would be about, I guess, 27,000. Is that the right way to think about this? Yeah, I think that's the right way to think about this. Make sure I'm getting this right. And then the idea being is that for every, as we increase total population, the slope tells us that the median income will be increasing as the population increases. That's what this number is here. It's the slope. We have some things like standard errors and t-statistics and then significance values. In this case, they're both strongly significant, which is telling us that, we believe that statistically speaking, these values are significantly different than 0, right? The hypothesis test says, do we think the intercept term is 0? Yes or no? Small p-value, no, we don't think it's 0. And similar for the slope. So even though the slope is quite small, right, it's 0.06, its standard error is even smaller, 0.002. That means I get a big t value, and that means I get a small p value. Again, I'm not going through trying to explain all of this stuff in gritty detail in this video. It's more so how to use R. Hopefully I'll have other ones popping up which will tell you more about what this means in finer detail. Anyway, we also get other things out, like the residual standard error here. We have multiple R-squared value, we have an adjusted R-squared value, we have an F statistic, we have degrees of freedom, we have another p-value. What's this telling us? Well, it's telling us that there does appear to be at least some type of linear relationship here between the two variables. It doesn't mean it's causal. It doesn't mean that if I take a small county and shove like 100,000 people into it, that we're suddenly going to have higher incomes, right? But it is telling us a relationship here. It's saying counties with higher populations have, on average, higher incomes. Probably because higher populations would correspond to cities. Cities have higher costs of living. Incomes need to be higher to counterbalance that, right? I mean, that's one reason, right? It's not necessarily a causal relationship. It's just noticing that this relationship does exist in our data set. The R-squared value here is just under 17%. So it's saying, okay, there is some explanation here of total population being used to explain the change in median income. But it's still a very small value. So it's saying there's still a lot of noise, right? There's still a lot of variance unexplained by just the total population. Anyway, another great way to look at this is to run back up here and use this plot command. So if we plot the data again, and I'm going to increase my window here so you can see it better, then what I want to do is I want to plot the line on top of the data. So I'm going to create my variable here, TT, which is just going to be a sequence from the min to the max population. So this is going to be like the X values where I'm going to try to draw my line. I create 200 of them. It doesn't really matter how many. It's a straight line, so you don't really have to do it this way. But I'm going to use the predict command next. So for the predict command, I'm going to give the linear model. And then I'm going to say, this is the model I fit. And here are the new data points. The new data points are going to be populations of the value TT. And I'm going to spit that in here to create a prediction. So that's what PRD is going to be. It's going to be predictions. Now, predictions are going to be happening on the log scale. So what I have to do is I have to do 10 to the PRD to take it back to the absolute scale. But then in the end, I'm actually plotting it on the log scale. So it's a little confusing. But in the end, what do we get? We get a straight line. This line is minimizing the squared error on the log scale between the line and all the data points. And there it is. It's increasing. We kind of saw that from the slope before, but it gives you a rough idea of what's going on. Right? If I have a population of about 1,000 people, I might expect a median income a little over, say, $40,000. If I have a population like out here in LA that's, 10 million, then, well, okay, maybe my median income would be expected to be higher, like 80,000. Obviously, there's some extremely high variance here. We have some counties with median incomes well over 150,000, or at least 100,000, probably closing in on 160,000. And then we have some counties with extremely low median incomes. I'm not sure what the minimum is here, but it does look fairly low down. So there's a big spread, basically. Again, it's good to remember that this is a linear model, but it's a linear model on the log scale. I can plot this exact same line, but on the absolute scale, and the straight line now looks something like this. So it's always good to know what you're doing, right? Here, this is still a linear model. It's just a linear model now transformed out of the log scale. And it looks kind of neat. But you wouldn't want to fit a linear model to data that looks like this directly. Because, well, the skewness, right, the way the data is set up is just not going to play nicely with a linear model. Right, you have most of your data points are shifted over to the left. You have this leverage point in LA, which is way out to the right, which is going to screw things up, right, if you try to do a linear model on this directly. Anyway, there's lots of little fun subtleties and techniques you can use to do linear models, and it's fun to play around. So now that you have access to this R code, you have access to the data set, I'd encourage you to try it yourself. You could try to predict, say, total votes, or which counties vote the most, or which counties voted the most or the least for Trump, or is it the rich counties, is it the poorer counties, is it the ones with more people on the census, checking off non-Hispanic white as their demographic category or not. There's so many things you could try and figure out, so go forth and do that. But before we're done, I wanted to point out that there's a lot of interesting R packages that have extended tools in them. So when you start R for the first time, going back to the beginning of this video, you're going to get some base packages, stats package, utilities package, some base ones. But there are some other really useful ones as well. There's MASS, which I forget what it stands for, but it's something like Methods of Applied Statistics in S. So R is, why is it called R? I should have started with that. It's called R because it came from S, another programming language, S being for statistics. I don't know if they have no, they don't have a documentation for mass. But the mass package has a lot of other really useful things in it. In particular, I'm pretty sure this is where the GLM net is. Is that where it is? No, maybe not. Wasn't there? No, this has negative binomial, right? This has some. So there's a couple other interesting things to point out here. So for example, in R, right, we have the GLM. We talked about LM for linear models. GLM, which is also in the stats package, is generalized linear models. But the mass package will also have things, I think, like if you want to do like negative binomial regression, right? So there's some other kind of crazy advanced regression methods that you could find in some of these packages. And the documentation is all online on CRAN, so you could always look that up if you want. A lot of these packages will also have data sets involved, like this one, which I think is this the one where they do the body temperature of beavers, I think it is. Yeah, there's some really interesting data sets built into R. So you can go find some, you can go find some data sets and try it yourself, like modeling the body temperature for beavers. Another one, which I hit the wrong command here, is lm test. Note that I'm using the library function to load in a library. These are already installed on my system, so I can just do that. Otherwise, you would have to install them first. I think mass is always installed. Lm test, I think you have to install manually. Anyway, lm test is useful because it has a lot of, well, linear model tests within it. So I think this one, you can find a lot of different tests for looking at trying to get, more information out of your linear model. Wald tests and coefficient tests and things like that. It's something you might be interested in. There's also the car one, which I'm pretty sure I never installed on my laptop. No, I never did. It's just on my main one. So this is actually a good example. If we want to install a package, we can use install.packages and type in the name of a package like car, and then we hit enter and hope that it works. Fingers crossed, because this is a live. Let's see if it's going to do it. Okay, looks like we're getting somewhere. Good stuff. So now it's going to just download all the packages, all these zip files. Eventually it's probably going to compile some stuff. If you look at R, a lot of R is actually written in like Fortran and C and other things like that, right? You don't actually want to do programming in R, right? If you're trying to invert a matrix using just R, you're doing it the wrong way, right? Because it's going to be super slow. You want to use functions, and the functions are, wow, there's a ton of stuff being installed. Why in the world is all that being, maybe I updated, I did not expect that. Anyway, we got a whole ton of packages now installed on my laptop. Good stuff. I think car, okay, they're not going to have a page for us. Car has a lot of good things too. I use this a lot when I do design of experiments because it has ANOVA type 2 and type 3 you can do. It has a lot of other things as well. Box-Cox method, that's what I knew there was another reason I wanted this one. The Box-Cox transform, which is a popular way of trying to transform. I guess this one is now defunct. So I think there's another Box-Cox, maybe it's capital B. Anyway, or maybe it's whatever it is, right? There's a lot of different tools you can use, like how to transform your data, different more advanced regression techniques, ways of computing like confidence intervals, right? There's a lot of good stuff. So it's good to, explore some of these packages, try to figure out what they can do, right? I think this one even has a discrete wave. Oh, that's Durbin-Watson test. DWT could be discrete wavelet transform or Durbin-Watson test, two very useful but very, very different things. Well, at this point, I'm basically just rambling, so I'm going to stop now. But hopefully this video would help you understand how to use R to just load in some data, do some quick commands, fit a linear model. But ultimately, the best way to learn this is to try it yourself. Right, download, for example, the R script that I wrote, find some other R code, play around with it, and see what you get, right? Because it's a lot of fun, but ultimately you're going to just have to try it yourself and see what comes out. So hopefully this was helpful. Let me know what you think, and see you in the next one.